All right, everybody, I think it's a good time to get started. Welcome to the first RI seminar of 2017. Today we've got Carrick Detweiler as a professor at University of Nebraska at Lincoln. He did his PhD at CSAIL at MIT, done a lot of work in field robots like underwater vehicles, air vehicles, for environmental monitoring and agricultural monitoring, and now we'll hear a little bit more about his fire prevention with UAVs. He's now a professor at University of Nebraska, and he's got his own group there doing a lot of cool things. So let's give him a little hand to welcome here to CMU.
Thanks, Steve. Yeah, so my name is Carrick Detweiler. I'm an associate professor at the University of Nebraska. And today I'm going to start out by talking primarily about some recent work we've been doing in actually starting fires with drones. But before I talk about that, and we're trying to start fires for good reasons, so I want to give a little background on wildfires and prescribed fires and why these are challenging and important things to work on. And then at the end of the talk, I'll also talk about some other work we're doing in my lab related to also field robotics, but also some techniques we've been developing more on the software engineering side to ensure that the software we develop as roboticists actually does what we want it to do, and that we can quickly identify and correct any bugs we may introduce. So a little bit about wildfire. So this is a huge problem in the United States, also worldwide. It has growing problem. You hear now, not just in the summer, but all year round, about wildfires, especially out west, that are just decimating areas. It's extremely dangerous, not only for the property and people who are there, but also for the firefighters who are involved. And they make huge use of aviation. So about 20% or 25% of the costs of fighting wildfires relate to aviation. So these are wildfires, so things that are basically, somebody throws a cigarette out of their car or forgets to really put out their campfire, or just parks their car too long over a grassy field, and the heat from the car can ignite these wildfires. Lightning strikes, the natural causes. So wildfire is something that naturally occurs and has occurred, and actually now we're actually seeing an increase in use of prescribed fire, which is where you're actually on purpose going out and lighting fields on fire. And in part, this has become an important land management technique, because this is what naturally happened. Lightning would strike and fields and forests would burn. And this would happen on a 5 to 10 year cycle. So every 5 to 10 years, most of the forests in the western part of the country and all of the grass in Nebraska would be burned off. And this was just part of the natural ecosystem. But as people moved into these areas, we don't like fire. We try to stop it. And this has then led to these bad effects. So increase in wildfire, while it's also coupled with global warming, is also tightly coupled with the fact that we've prevented fires on these lands for too long. In Nebraska and elsewhere, it turns out there are a lot of invasive species that were previously managed by fire. So actually in these pictures, all of these green trees, these are red cedar that are considered an invasive species in Nebraska and elsewhere in the Midwest. They basically would grow everywhere if we didn't spend a lot of time mechanically cutting them down, or if the better way to get rid of them is to burn them, because they burn quite readily. So fire, while it can occur in what we consider wildfires, which are often viewed as bad, it's a critical part of the ecosystem, and now we're seeing increased use of prescribed fire as a way to manage these. But there are significant costs associated with these. So fighting wildfires and basically using prescribed fire, it's about $3.7 billion a year is what we as a country spend on fire. But if you look at the larger economic impact, it goes anywhere from 50 to 100 million to some say $200 billion of economic impact in terms of the houses burned down, but also the resulting impact of having people evacuate. So this is huge costs. As I said before, 20 to 25% of the costs here are associated with aviation. And in part, that's a high cost because getting a helicopter out there is very expensive. And while they're very expensive, they're actually the types of helicopters and the crews that they use for these are often not available when you need them, just because there are so few of them. And that's some of the economic costs, but this also has, beyond the economic and property costs, it's a high-risk activity. So 15 to 20 people die each year, and these are firefighters going out to fight these fires, but also firefighters just lighting prescribed fires, which is relatively safe compared to fighting wildfires. It's still a dangerous activity, and about 25% of these deaths relate to aviation. So what we've been working on is the development of an unmanned aerial vehicle that can really try to remove people from these dangerous situations. So this is a prescribed fire that we worked on with a group of landowners. And here, in this area surrounded by fire, all this dark is the smoke from the cloud, is this guy driving an ATV with a drip torch to ignite this interior portion of this prescribed fire. So this guy, okay, these people like to do this, some of them. Okay, actually one of the firefighters told me he'd either be in jail for being a pyro or he gets to light fire as his job. So some of these people like to do this, but this is extremely dangerous. So what we've done is developed this UAS or UAV that can actually ignite these prescribed fires. And last spring we did the first successful outdoor tests of this, the first test ever of an unmanned vehicle to actually ignite fires. And what I want to talk about today is a little bit about how this project got started, and then go into some of the details of our field trials and how the design of the system has evolved over time. Hopefully as field robotics people, or just people interested in robotics in general, you can learn a little bit about kind of the evolution of this and how this project came to be. And then I'll also talk about a few other projects and what we're doing in the future. So it turned out that the way we got started on this project was actually related to a different project we were working on aerial water sampling. So this is a video of how you traditionally sample. This is looking for another invasive species of mussels. So they do these little tow net things where they throw these out and look for the veligers, the little baby, almost microscopic mussels. And what we did in this project was actually develop a UAS that could go out and collect water samples from the air. So getting to areas that would otherwise be hard to access. You can't put boats in these waters that you think have these mussels, because then you'll spread it to any other ones. So we developed this vehicle that could go out, basically has a pump on the end of this, and I'll talk about this more a little later, and filters the water through a filter that we can then look for the veligers. And it turned out with this water sampling, we were working with Craig Allen, who's a natural resource ecologist. And as we were talking over lunch one day after some of our water experiments, he was talking about this other guy, Dirac, who had just joined the university and was a fire ecologist. And we started thinking about, okay, and then my colleague, Sebastian Elbaum, who co-directs my lab with me, we were talking about, okay, well, there are a lot of dangers in doing these prescribed fire ignitions. Can we do this with a UAV? My first response was, you're crazy. In part, this was because at the time we were just going through all the hassles of dealing with the FAA and doing things the right way to fly legally, and I was already had enough paperwork. But we had a few more coffees and lunches together, and decided, okay, this might work. This could work. So a while later, we basically quickly prototyped a system to actually do ignitions. One of the things we did was we used these little spheres. These are called PSDs, or plastic sphere dispenser balls. And these are basically ping pong ball sized balls that have a chemical inside, potassium permanganate, which when you inject with glycol, about a minute later, it causes a chemical reaction and fire. So these are actually used commercially by full-sized helicopters dropping these to light these prescribed fires and also for use in wildfire fighting. So these were known by the firefighting community. So we developed a quick system to try to deploy these and do some ignitions. It worked. After that, we started developing. We actually had some people involved in working on this and developed a number of different prototypes of the system over about 9 months or so. And then we started doing some tests of this indoors. So you can see that's the fire from these PSDs. We were working on, the hardware, but also the software. How do we do this robustly, reliably? Basically, and this is just showing, how it's done traditionally with these drip torches. They're just manually lighting fires using, putting it out. But this is also just to give you a sense of the full-size helicopter. This is how one of the ways they do it at large landscape sizes. So basically, we did some indoor experiments, and this was, early 2015. Looking at how we can coordinate multiple vehicles, do some of the planning and system navigation. And really, this was all for prepping for our outdoor experiments. So we did a lot of testing indoors, a lot of evaluation, seeing what works, what doesn't. But then we also had to, when we were saying, okay, we want to go do this outdoors, turns out that you have to get a lot of permissions from all sorts of people to make this happen. So this was, both working with land managers, people who are actually doing this. They actually were really excited and engaged to make this happen. But then we were going to do this on some federal land. So it turned out that we had to get permission from everyone, including NASA. Seriously, we had to send in a 100 to 200 page document to NASA, because it turns out that the Department of Interior that we were working with has NASA certify the airworthiness of their aircraft. So so they don't just do space shuttles and things like that. And this led to our first test this past spring at Les Canyons, which is in central Nebraska. Again, this is one of these areas where they have a lot of these invasive cedars, and basically landowners in this area get together and they have these burn associations where they go through and will do these prescribed fires, trying to get all of their land burned every 5 to 10 years. And they do this. And so this was a 2,000 acre burn, which is a pretty good sized burn. That's, let's see, about 2 by 2 square miles, or 2 miles by 2 miles roughly. And we were targeting just a little small part of it, about 150 acres. And this was at the very end of their burn, where we were then igniting these canyons. So here you see our vehicle, which is now, the third version of this vehicle, and basically flying out about 400 meters to this ravine, which you see here. And this is actually fairly deep, and the other way they do this is basically they send a person with a drip torch down there with an ATV to do the ignition. Again, this is something that can be very dangerous for people who are driving there. Most of the time, it's perfectly fine. They can do it quickly. But if the ATV breaks, something happens, they tip over. These things catch fire very quickly, and so you have very little time if something goes wrong. So here you can see, with the smoke in the background, the vehicle going along. And then towards the end, we come back, and this is actually the fire that we started. Now going up, this is a few minutes later. So we sent out, dropped some of these ignition spheres, come back, and then about a minute after this, we had to move back another 500 meters because those flames get so big and hot that you have to be pretty far away. So this was our first field experiment where we weren't just doing indoor ignitions or doing drops outdoors, but really where we were actively part of a larger prescribed burn. And this was largely successful, but we also learned a lot from this experiment. A lot of the things we learned were relatively minor. Things like the fact that we had to be out there by 6 a.m. And they started the burn at 8 a.m. and they're like, okay, well, you'll probably start a few hours later. Turned out that the wind had shifted and it took 8 hours for us to get started. So we were all set to go at noon, and then we didn't start until about 6. So a lot of these things. But then we just had about 10 minutes before they wanted to continue on. So a lot of this hurrying up. It turns out that most of these landscapes, you just drop one of these ignition spheres and it'll start. We were thinking, okay, we need to drop dozens of them, things like that. Our major lessons learned were just, obvious in retrospect, but things just like the dust and dirt, and we were using a system we had already injected hundreds or thousands of balls with. We had some jams at the end, so those were some problems. The other thing we learned, which we then modified for the next version, was that largely the way these people work is they point. They say, we want fire over there. No, a little left. So for the second, or for this, I guess the third version, but the second field test, we just developed a very simple interface that allowed much easier interfacing of the pointing from the burn boss. And this was for a test that basically was a month later. We ended up actually doing a almost complete redesign of the system to eliminate jamming and updating software and other things. And this was for a test at Homestead National Monument. So this is a national park in Nebraska. And this really, there were a whole bunch of firefighters involved, but this was really, they were letting us evaluate our system versus how they normally do it. So here you can see the vehicle dropping the ignition spheres. This is a view from an onboard camera where it's injecting and puncturing the ball and dropping. And so this is just a useful view to see where you're actually dropping these. But then also this is flying back afterwards to see actually how the fire spread from these balls. So this gave us some information on, okay, where were we, did all of them ignite? How long does it take to actually spread? These types of things to help us characterize it. We're also looking at things like what's the air temperature, where we're flying, estimating winds and things like that. So the result of this experiment was quite good. So we directly burned about 20 acres, which was almost this whole area. You can see this, just maps of different lines of fire that we tried doing. And this was, again, largely directed by the burn boss, the firemen in charge of this area. And we were just looking at how this spread. One thing that we learned, again, we're not quite fast enough. So we had a much fewer balls, which from our first experience, we didn't need as many ignition spheres as before. But that meant we were coming back to reload more frequently. We had it down to just about 2 minutes to reload and launch the vehicle. But even that is not necessarily fast enough. So next time we go out in the next few months, we'll have a pair of vehicles so we can have one ready to go immediately upon coming back. Also, interfaces can always be improved. But the good thing is we didn't have any jams. We didn't have any problem with dust and dirt and contamination causing problems. So this system is now has become much more mature and has been doing well. And let me just give you a little bit of an overview of some of the design details. So there are a few main components. There's the hopper that actually holds the balls, and it turns out that these are interesting balls to dispense because they're ping pong balls, but they have a little, basically like sand in the bottom, so they don't roll easily because of the dynamics of this stuff that doesn't, it's not a uniform ball. So we've gone through a number of different hopper mechanisms. One of the key things is just having a quick release on the system, both for us to be able to quickly remove it, but in case there is a unintentional fire, we can remove it or drop it quickly. Piercing, so these balls are, you can stand on these on concrete and they won't buckle. So it requires quite a bit of force to actually pierce these balls to inject the glycol, this liquid, into it. Some of the things we did, so we went from our prior prototype where we could hold about 40 ignition spheres to one that just held about a dozen. One of the reasons we did this was just flight time wise. We didn't gain much by adding more. But the small things in the design, like just having the center of gravity over the appropriate place to make this work well. And this video shows a little bit of the system. So again, this is a modular system you can easily attach or detach. Then we have this this mechanism so to load the next sphere in, and then we drive this ball on a small needle up there, and then we inject it with the glycol to actually cause the ignition, which happens about a minute after the injection. So we have time then, we have about a minute to get it out and drop it out so that we can safely move on to the next location. So this design has been quite successful, but really there were a bunch of faculty involved, but these are the 4 main students who were really doing much of the work on this project. So we had a pretty interdisciplinary team of a mechanical engineer, an electrical engineer, computer scientist, and a computer engineer all working together to basically work on the different aspects of the system to quickly get it up and running. And a lot of this, so we did the first prototype in just under a week, a few days of just prototyping, and then we had a number of iterations, and a lot of this was built on the software and systems we've developed in the Nimbus Lab, which I co-direct and co-founded. Now we have maybe 20 or a little more than that students in the lab, and now we just hired a year and a half ago 2 new faculty, so there are 4 faculty co-directing this lab. And really our goal here is developing this type of UAS system to get closer into and interact with the environment. And what I want to do now is shift a little bit away from fire and talk a little bit more about water sampling and some of the other projects that we've been working on in the lab that really laid the foundation that enabled us to fairly quickly develop the prototypes and evaluate the proof of concepts of the fire ignition system. So, as I said at the beginning of the talk, this really came out of a project we were doing on water sampling. And the reason we were doing water sampling is places like this. So this is a site in Nebraska. It's actually the 2nd biggest recreation site in Nebraska, about an hour from Lincoln, where I live. And okay, can anybody? So these are all the little lakes. So why are they all these strange little lakes here? Anybody guess?
Fishing.
Fishing, yeah. So they do a lot of fishing. Are these natural?
Kind of a dam downstairs.
Okay, dam. Who's driven through Nebraska? Okay, the 2 Nebraskans. Okay, so they have this highway drive going through Nebraska. They needed sand to lay the foundation for the highway, so they dug a bunch of pits here, not too far from the highway, to get the sand. And then they said, oh, okay, we have a low water table. They fill up with water. Now this is a great site. People have houses around this. People have go fishing and all these things. Turns out this is an interesting site because while these are all really close to each other, okay, so this is 500 meters, so these are really close to each other. It turns out that there's some strange interactions with the water ecology between these. So I don't know, a half dozen years ago, there were some toxic algal blooms in just a couple of these little lakes or ponds that killed some dogs and fish and all these things, so you couldn't swim in some of them. But it turned out that of these like 20 some odd lakes, only a couple of them had these problems. But in order to manage this, you have to collect water samples and analyze the water quality of all of them because they're somewhat independent. So this is a very labor-intensive process to collect water samples. There are automated samplers that you can deploy, but they're quite expensive and still require regular maintenance and somebody grabbing them. So they still largely rely on manual sampling of these lakes. And so some colleagues of mine who are water scientists were doing this, and it was taking them 12 hours to collect samples from these 20 lakes. And most of that time was actually putting the boat in the water and taking it out to get out to the middle of the lake where they could collect a clean sample. Very little of it was actually the sampling time. So what we did is we actually developed, again, a UAV and that could go out and get close to the water and collect water samples. Now the challenges here were both in the mechanical design, which I'll talk about a little more, but also in how do you safely actually fly close to the water where the onboard altimeter is not precise enough, and you have a lot of errors and sensor noise, and of course the cost of failure is high because if you don't get things right, you fall in the water. So we also were focusing a lot on, again, developing software tools that would automatically analyze the code we were writing, but also the system performance as it was going on to enable this autonomy. So just to give you a little bit of a mechanical overview of the system. So we have 3 water sample chambers in this particular configuration, and then a little needle that can rotate to each of these chambers to fill. Importantly, we also have the ability to go in between the sample chambers to purge. So you don't want the contaminants in the tube from one location actually contaminating the next sample. So going from these little lakes, you can hop from one lake to another, basically park in the middle of that area and reach all of them. And you want to make sure you purge between samples. And then of course these are vials that are quickly changeable. So that 12 hours, instead of taking 12 hours, it's possible to get that down to just a couple hours of sampling. We have a lot of sensors on board, including a pair of ultrasonic sensors just for range finding. Also, just some exposed wires that allow us to measure the conductivity, so we know that how deep the tube is in the water in a very low cost, easy to use method. And then as you saw in the video before, we've been able to do a whole lot of field experiments with this system to collect water samples in a at least semi-autonomous way, where the scientist is the one saying, okay, I want to sample from this location, but then the vehicle goes out to that location, goes down to the water to the right altitude, and then can collect up to 3 or more water samples depending on the payload configuration. So here you can see the vial filling as it goes. So this project started a few years ago, and we've been working with a lot of water scientists on this project, and some of our collaborators at UC Berkeley. This is an experiment we did with them where they deployed these hobo sensors and static arrays, and we did comparisons on how the measurements from those sensors compared to our measurement locations taken over time. And what we can do is now, in this system, we weren't collecting water samples, but actually measuring the temperature profile. So here from the air, we're able to measure from the surface of the water down 2.5 meters to get the temperature profile. And from that, you can then reconstruct the 3D temperature map of the system. Now, what's really exciting is that we did these experiments with them, but now this past summer and fall, their team was actually out there without any robotics people flying a UAV collecting temperature sensor reading. So this, for me, was the point that I say, okay, we succeeded in something. If we can actually get the water ecologists, those scientists out there flying these systems and collecting meaningful data, that's a real success. Now, we've also done some other more controlled experiments with the University of Kansas, where they have all these tanks with various configurations where we could actually at least somewhat control these tanks. So we went out and they actually had, we had some control tanks, but then we had tanks that we actually pumped salt water into the bottom of them, so we had a strong conductivity gradient in there. We had some that we actually put, so these ones, big blocks of ice down at the bottom so that we could get a strong thermal gradient. And then we went out and actually did comparisons with our UAV versus the traditional method, so actually using static sensors in place versus putting a sensor in manually. And we did this both at these controlled tanks, but also larger, at a larger pond they had there. And it turns out that we're actually almost an order of magnitude faster than the traditional methods, at least for these types of systems. And so this was a whole lot of flights, 60 flights in a couple of days doing a lot of these experiments. So this is, I guess, one of the projects that, again, had some direct lead into the development of the prescribed fire vehicle, but also is really, a lot of the software and systems that we used were about the same. Okay, but now I have a question for everyone from, I guess this is now a year or so ago. What's this picture from? Anybody know? Okay, this was in a lot of newspapers for a little while. What? White House, yeah. So this was the Secret Service agent who crashed their drone while intoxicated, possibly on the White House lawn, right? So, okay. So failures, I say, are part of field robotics. So who's had a robot crash or fail? Okay, come on, everybody, right? So we've also had our fair share of crashes. Yeah, so this one, motor failed to start, and we were using this great hex rotor with propulsion redundancy. You could stop. If the motor failed mid-flight, it would still fly. We tested this. It turned out that they had a bug in their software that on motor start on takeoff, they were not checking to see if a motor failed. So, their software returned a yes, motor's working, motor started, flag to our software, and we took off and crashed. So, so this is, one of the things that has motivated a lot of the other work that we do in the lab that I'll just touch on briefly, which is trying to avoid and identify failures in robot systems. And I think there are a lot of reasons that robots fail. So hardware or software, these are definitely two key things. Environmental conditions. I like to tell my software engineering colleagues that I'm a perfect programmer. I never have any bugs in my software. But okay, that might not be true, but I think a lot of failures in robot systems are just not understanding the environment you're operating in. So there may be unexpected things that happened. It's too windy, the lighting is incorrect, things like that. I mean, the first prescribed fire system, when I built the system, I had used a IR little detector as an encoder to know when the ball was in place. Well, we went outside and it was really bright out. The sensor was saturated, it didn't work. Fortunately, we had a roll of duct tape, could cover it and make it all dark, make it work. But there are a lot of problems, and including things like users inputting incorrect commands or just not really understanding the limits or the parameters for systems. So one of the things we've done is develop tools to help debug some of these complex systems. So we just did a little survey, and the Arducopter, this open source platform for UAVs, they have about something like 622 parameters that the user can configure. And this is not the developer can configure, this is the user, okay? Now, similarly, okay, so ROS, navigation when we did this had 220. Okay, these are a ton of parameters, and I don't think I could know what 600 parameters mean if I developed the system, let alone if I'm picking up somebody else's software. And it turns out that this 10 to 30% of questions on the Arducopter forum involved questions about what does this parameter mean, or why this isn't working, and someone says, oh, you just need to tweak this parameter. So there's lots of these parameters that just need to be tweaked. So what we did was developed a software tool that let a human and some automated software tools we developed interact to actually help figure out which parameter might be causing problems. And in this work, what we did, just to give you a brief overview, is we developed some tools for ROS that could automatically analyze the code and figure out where there were parameters, ROS param, sets and gets and things that the user was using as thresholds in the program. And then what we could do is, while the system was executing, while the robot was flying or driving around, the end user could then say, mark two types of errors. One, which we call type 1, is the system didn't do something it was supposed to do. So the robot was supposed to drive out the door, but it got to the door and stopped and couldn't get out the door. So that we consider a type 1 error. Type 2 errors is that it did something when it shouldn't have. So okay, it got to the door and turned around and went back instead of going out. And what we did is, just using those two types of tools, we've developed the software that can then basically, when the user flags this as a problem, the software then goes and says, okay, are there any thresholds that may be involved based on these configurable parameters that could be causing this problem? So here, this green line represents this configuration parameter. Here, the software or the sensor value relating to that threshold was going down. It crossed it, and at this point later, the user marked an error. So what this means is that maybe this threshold should have been down further so that it didn't get crossed at this time. And basically automating how this analysis goes, so that basically the user can mark errors and then automatically come back and present the user with, okay, so you said something went wrong. Maybe it's one of these two parameters that caused a problem. And with this, we've only done relatively small studies of this so far, but users are able to actually correctly identify which parameter caused problems. We're also developing some other techniques in terms of identifying sensor rates and how they propagate. So what happens when you go from a 30 hertz frames per second camera to a 60 frame per hertz camera? Does that, what nodes in your system in ROS does that actually impact? Do you have to consider the effect of this on your whole software system? Probably not. Well, we've developed some tools that say exactly which parts of the system you should analyze to see how this rate change could impact it. Also, things like automatically detecting problems with units. So in this bottom example, this is so this is real code on the ROS repository, where basically somebody has a typo where they forgot to square the meters terms at the end here. So you're trying to add meters squared with meters. Now the compiler won't complain because you're just adding two floats together, no problem. But robots that have physical meaning, we can derive these units based on the fact that these are a geometry message in ROS, which has meters units. We can detect these types of bugs. So these are some of the other things that we're working on in my lab in terms of developing these tools to debug these types of systems. So I think just in summarizing some of this work, I think that a lot of the focus of my work is what can you do with UAVs when you actually get closer into the environment. So we don't just fly high and take pictures. There are a lot of interesting things you can do with that, but I think once you get into the environment, it's a lot more challenging, but also interesting to work in. And I think that this is where UASs will transform a number of new fields in the next 5 to 10 years when they really are starting to interact with environments, and like a lot of the work here as well, navigating challenging environments with vehicles. I think there are also some real challenges with this in terms of public perception and privacy, also regulations. Things are changing, often or sometimes for the better, sometimes for the worse in terms of what we can do with these things. But also, I think it's important. We're doing some studies on what the public perception of these vehicles are and tracking it. So have done surveys the past 3 years to track how public perception of drones has changed, and to see how this is going to evolve over time. And just a little bit in terms of how we're moving forward. So we're now going from the vehicle down here, which the Firefly from Ascending Technologies that we worked last year for the prescribed fire. We're going to a Matrice 600 for tests we're doing in the next few months. So much higher payload, so we'll be able to fly for 30 minutes, dropping hundreds of these ignition spheres to do this ignitions on larger systems. Also integrating map interfaces in addition to kind of these pointing interfaces to give the users of the system a lot more flexibility. We're also the kind of more of the computer science angles that we're looking at right now are using onboard sensors, so actually measuring the temperature gradient in the air with a bunch of just temperature sensors to try to detect if we're flying into a plume of smoke or hot air that could cause navigation challenges to the vehicle, or actually burn up the vehicle if we're too close. So looking at how we can actually detect that and replan where we should be going, and in part to at least move towards increasing the autonomy within the constraints of this prescribed fire and wildfire community, which they are sometimes slow adopters of some of this technology. So we'll be doing more tests in the next few months. We have a lot of burns lined up, so I'll know more, I guess, by summer how things go. And of course, there's a lot of people to thank, not only for the prescribed firework, but everyone else. And then I have just one question. Okay, so who are the computer scientists and who are the firefighters? That's my. Okay, yeah. So next time before I go out, I'm going to roll around in the dirt. So that's another lesson I learned. So with that, I'd be happy to take any questions.
So I got a question about, I guess, the autonomy. I mean, both in the firefighting and in the water sampling. Do you think there's scope for sort of improving the performance of the overall system by understanding the robot understanding the environment and making decisions about where to go and where to sample, where to drop these things, and monitoring how everything's going? Or is it always going to be the domain expert that has years of experience that knows how to do this? Is always going to be
Yeah, so that's a good question. So I guess the question is, how much the onboard autonomy can actually help, especially in these field domains where, the scientists, the water scientists, or the firefighters, they have a lot of domain knowledge that I think is really hard to encode in a program. So I think it's always going to be, more of this mixed autonomy where I think we can do a lot of things concretely, very quickly, and make decisions much faster using autonomy to, I think, again, try to prevent these problems that are easier to encode or detect. So make sure you don't fly into an area that's too hot, or or saying, okay, we're not going to drop an ignition sphere on an area that's already burning or has already burned. I think those things we can do pretty well. I think we can also do some of the planning for at least some of this. So the prescribed burns, there's some pretty basic approaches to how you do these burns. And I think we can encode a lot of that. But I think the key is that we need to be very flexible and quick to react when the user says, no, you should be doing something else. And maybe this is just getting approval for any changes, or even better is just allowing the user or the firefighter to say, no, do something else. But I think the key is that we need to be able to react fast to that, to basically not do something we shouldn't be doing. Yeah?
In your project for sampling, collecting water samples, the hanging tube, did you have any problems with that? I mean, did you plan your design such that it somehow doesn't affect any dynamics or causes problems while moving?
Yeah, so the question is, does the tube, how much we planned for the dynamics of the tube? And yeah, I mean, so we actually tried a bunch of designs. I mean, so there's been some great work in terms of dynamic control of these suspended loads below vehicles. We purposefully tried to stay away from having to integrate those types of controllers into our system. And what we found is that with this tube that's somewhat flexible, and the pump we have on the bottom is actually pretty small and lightweight. We also have a peristaltic design that the pump is actually up at the vehicle. The dynamics of the tube don't really impact the flight of the vehicle. And we've done this even with like 4 meters, 5 meters of tubing hanging down. It was definitely one of the things we were really concerned about at first. We had actually initially tried, our very first water sampler consisted of a rod hanging below the vehicle with a little vial. The vehicle flew fine when the vial was empty. When we got water in it, the controller oscillated around it, which made for some fun flying. And that was our kind of weekend prototype. Okay, this might work, but we need to address some of these issues.
So going with the flexible one?
Yeah, so this semi-flexible tube helped. It's much easier to fly with this tube that has, it has some dampening naturally than flying like with a weight suspended on a string, where you can end up with some really strange oscillations that can cause problems.
Were there any stability problems regarding with upward thrust from the heat of the fires?
Yeah, so that's a good question. So the question is, were there stability problems with the updraft from the fire? So this is something that we were concerned about. We're a little less concerned, but still something we are actively collecting data on. So definitely these fires, they cause large updrafts. And there are actually 2 problems that can occur. So there's the actual updraft, but then there's actually the pressure change. And since we're using a barometric altimeter, that can then influence the altitude that it thinks it's at. We have not pushed it to the limit, but we've done some flights over these fire lines at 10 meters or so, and we didn't see much of an impact. And actually at that height, for these flame lengths that were just a few feet, the temperature was only 3 to 5 degrees Celsius higher than the ambient temperature. But this is definitely something we're continuing to monitor and look at, and both in again, integrating onboard temperature sensing, but also so we'll see, I guess, how this reacts when we start to try to fly closer to the fires.
What happened when the ball got jammed on your copter? Was the glycol in the ball, or was it?
Yeah, so on the first field test, it ended up being the last ball we were deploying. It did jam after it had injected. Our software reported that it jammed. We couldn't get it unjammed, so fortunately we were within about a 30-second flight back, so we flew it back to us and were able to get it out before it caught on fire.
So the quick release can't release in the air? It has to be manual?
So we've had a couple different designs. The one design, actually the one that jammed, we had basically a little string as a fuse. So if the ball ignited, it would break that string and it would fall. The whole unit would fall. Which in the context of these prescribed burns is fine, because if you drop something that's on fire, that's fine. In the latest revision, it's a manually actuated. We can also, we've added a servo just to automate that release. But we also have basically a pretty thin grate of ABS, 3D printed part below it. So while we haven't tested this on the vehicle, we expect that it'll melt through there before it causes too much of a problem. Yeah.
So with your software testing, system verification tools, like, I guess how far have you gotten from the conventional way that everybody's works without really having any understanding about how things are done in the system so where are you right now? How far have you got along?
Yeah, so the question is how far we've gone with kind of some of the software testing tools. There's still definitely research prototypes, so primarily, we're analyzing code for specific projects, but we don't have a great, okay, here we're going to run these 10 tools against all of our software yet. But they're getting more mature, and I think definitely there's a lot of differences from the traditional software engineering techniques that are designed to run on Apache web server and Microsoft Word and things like that, versus robot systems where, again, I think a lot of these faults are in configuration values, or that may only become apparent when you operate in different types of environmental conditions. So I think there's there'll be a lot of utility to these types of tools soon. So. Yeah?
Just as a comment, I want to say that it's outstanding that these burns are actually getting done. I remember 20 or 30 years ago, this was just being discussed, what a good idea it should be. And then now we see, lots of people getting killed doing it, and it's in the paper all the time about firefighters dying and whatnot. So this idea of being able to just, get these control burns done before they turn into some kind of holocaust or whatever is really good progress.
Thanks, yeah.
So, but if you wait and it turns into the Yellowstone fire, and you've got millions of acres burning, and it's a mess.
Yeah, I mean, I think there's been, and it's still a slow shift, but there's been a lot of recognition and shifting, and like saying, okay, fire is natural, fire is something
Let's get this done.
we should use instead of trying to keep at bay. And I think, we'll just see this continue to.
And this is really dropping the cost and the human risk, and making it a lot easier to get it done.
Yep.
Any other questions, or maybe we could come to an end there? So let's thank Carrick one last time for